All right. Good morning. Today is January 12th. My voice is almost completely back. So we're right here, which means that we technically have two tutorials due this weekend. I'll probably extend the deadline of tutorial 2, right, to here. Just, don't let it interfere with finishing your assignment either. Yeah, so this weekend, though, for sure, tutorial 1 will be due. Tutorial 2, I think I'm going to extend it, just to give you guys the option. And then, of course, well, it's just 2 weeks, and then assignment 1 is due, and then test 1. And so what it looks like is happening with test 1 is that, at least the plan is, if the budget is approved, it's going to be written in class with COMAS on your computer. Basically, it'll be, and if that doesn't happen, I'm going to give you a paper version of the same tests, right? So there's a test that exists. I'll either put it on Brightspace or I'll print it out. There'll be some coding questions. And if we do it with COMAS, so you're just going to either type the coding answers into Brightspace, or what I would advise you to do is I will also give you some files. You can load them up into VS Code, and then you can write the functions that you're supposed to, but also test them, right? So you can also run them and test them, make sure that they work correctly before you copy and paste them into Brightspace, right? So that's the general idea. I have to wait to see what happens with COMAS, whether or not I get approved for that or not. But that's the idea. So regardless of whether we use COMAS, it'll be the same test. You'll be asked some coding questions. Either you handwrite them for answers, or you type them up. And of course, in the case that they're typed up, we're going to be a lot more strict about things like syntax, right? So you will lose marks for not getting correct syntax. If it's handwritten, then we're going to be a lot less strict about that sort of thing. But you still should get the ideas correct. All right, so that's sort of where we stand. Any questions? Okay, so last class we were talking about basic language features, and we had talked about arithmetic operations. And incidentally, like this is, I mean, I sort of said this will be review for a lot of you, but I kind of think this is really sort of very important now. Now that you're no longer, I mean, the way things are moving, writing code by hand is sort of passé, right? You're going to be talking to a large language model, and the large language model is going to be translating your English into code. And so it's a lot harder to learn code when you're not writing it. So actually paying attention to these fundamentals is, I think, moving forward going to be very important. But regardless, we looked at arithmetic operators, and then languages, C++ in particular, but languages in general have what are called expressions. And an expression is just something that evaluates to a value, right? So it could be anything, but here I have a sequence of operators that, 2 plus 2 is 4, minus 3 is 1, so that evaluates to a value. I can integrate variables with that, so 3 times whatever variable is equal to, or the return value of a function, right? So if a function has a return value, then it also doubles as an expression. And then so that expression combined with this expression multiplied together gives us a new expression, right? So expressions are just a sequence of operations that resolve to a value. Expressions are typically embedded into statements. They can be standalone statements, like a function call is a standalone statement. I could just discard the return value. But I can also embed them into a statement, right? So, sorry. They can be standalone statements like this. This is technically an expression, but it also accomplishes something, right? So this will return the value of v, but in the meantime, it also sets v to some value. This just executes whatever code happens to be there, and same with set value. I don't think this example is particularly interesting. Other than this idea that, okay, so here are 4 ints, and we set 3 of them, and we print them out, this is a valid statement, right? It doesn't do anything. It evaluates a bunch of math, and then that value is returned and discarded, right? So expressions can be statements even when it doesn't make sense for them to be statements, but syntactically this is fine. The compiler is not going to complain about this, but this does not change the value of any variables. It doesn't change the value of any data anywhere. So it's sort of a pointless statement. Whereas I can take the same expression and embed it into another statement, and now it's useful because this return value will be printed out to the console. Or I could take this same expression and assign it the value that's returned to a variable d. But this itself is also an expression, right? It also returns a value. So this will return the value of d, well, or more accurately, it will return the variable d. And then, so in this case, this will return the variable d, and then we'll add 10 to it, and then print out whatever that result is. This is also an expression, etc. I don't think we need to run these, but that's just, yeah, sort of another property of C++, and usually a property of languages in general. Questions? Okay. So in addition to statements and expressions, we have control flow, right? So we don't always want to execute all the code all the time in a linear fashion. Sometimes we want to only execute code if a certain condition exists, or we want to repeat it. So we have these control flow statements. If else, switch statements, do while or for loops, and then these, which are ways to break out of loops or continue a loop, right? And so that brings us to blocks, and blocks is an example of scope. So this is sort of important, right? So once upon a time, you've seen sort of examples of assembly, and basically the control flow for assembly is the jump statement, right? So when people started first making programming languages, they used goto, which was sort of analogous to a jump in assembly. There's really not like for loops and things like that in assembly. Everything is sort of predicated on that jump and just using it correctly to construct these other things. But what was discovered at some point was that you don't even really need a goto, right? If you have blocks and control statements, you can do everything that you would normally do with a goto statement. So a block is basically a set of matching curly parentheses. For example, this for loop, its block is here, right? This is the statements inside the block. This is the beginning of the block and the end of the block. In C++, we have, of course, blocks for loops. We can have if, then, else statements. We can even have a block for no reason. And each of these blocks has what's called its own scope, right? Which means that in some sense, it's almost like its own function call in that I can declare local variables, and those local variables are valid inside that scope. So from the point where I introduce this variable to where I see a closing brace, this variable x is valid. But as soon as I see that closing brace, that variable x is no longer valid, right? So that leads us to this idea of that, well, here I declare an int x. I assign it a value 8. I'm assuming it's in some sort of scope, right? Not shown here is the main function. But then inside the for loop, I declare another variable x. Incidentally, what gets printed out here at the end? Right, so at the end, we're sending x to the standard output, and so what value should be printed? Well, we can run it and find out, actually, so let's do that. Okay, so we have something similar, but not quite exactly the same, and we're going to demonstrate a few extra things in addition to what we saw in those slides. So here I've declared a variable at what is called file scope, right? Which means that it is outside of every block, including the main block. So it's not in a function. It's definitely not in the main function. It's not in a class. It's just out there on its own. And this is a global variable. Now inside my main function, I declare again a variable x. And I assign it the value 8. And then I declare some other stuff, which is not super useful. And so then when I print this, well, I have two variable x's now. One is at file scope and one is at main function scope. And this variable x will hide this variable x, right? It's called shadowing. So when I shadow a variable, that means the original variable is no longer visible in that scope. In other words, when I print x here, let's just comment all this stuff out. I'm going to get 8 rather than 10, or I should, right? So, right, so the first x is 8. So it's reading this x, and this one is in some sense invisible, although it's not completely invisible. But when I write it like this, it is. We're going to see that we can actually access that global variable at any time. The questions so far? Okay. All right, so then we're going to do, well, in the code we used a for loop. Here we use a while loop, but it's essentially the same thing. And inside here, I'm declaring a new variable x each time. I'm assigning it the value y or I, and then I'm incrementing this variable. And then down here, I'm going to print out x again. And so size is equal to 5, but what's going to happen here? Well, the first x is 8 and the second x is 8. Because this x is actually a third x that is separate from the other two, right? So this x shadows both this one and this one. So that means when if I do something like, well, every single block, I declare a new variable x, I assign it the value I, and then as I exit the block, that variable is destroyed, right? So this x is sort of, well, at least the way we use it here is pointless. But we are not modifying any of these other value x's. If I did this instead, well then now I'm actually accessing that value x from the main scope, right? So my second x is now 5. All right, so that is each scope, right? You could think of it as being nested. So this block is nested within my main block. Any variables I declare in here are going to take priority over variables declared outside of that block, at least within the block. Once I exit the block, these variables in here are destroyed, and now this is back to referencing this one. Okay. And then finally, well, that first x that we declared, that global variable, it's sort of special in C++. In that I can actually access it whenever I like, right? So even though it's been shadowed here by this x, I could say, no, go right to the global variable x and grab me the value from that, right? So if I run this piece of code, that last x is 10, which corresponds to the value that we gave our global variable. So again, this is called the scope resolution operator. These two colons, they are quite useful for resolving naming collisions. You've seen how or perhaps remember how we use the standard namespace. If we didn't scope in the standard namespace, then we would have to put, for things like cout, we would have to do this. So we're going to see a lot more of the scope resolution operator as we move forward. But we've seen two uses. One is for namespaces, and the other is for accessing global variables. All right, questions? Easy stuff, right? Okay. Oh yeah, this Well, yeah, we could also do this in C++, right? Just int x equals 11. So I could put a block wherever I like for no reason at all. And that introduces a new scope where I can declare new variables. If I did not have this block here, then I tried to declare this x. Well, you'll see that, of course, I have an error. I'm redeclaring this variable x. So within this scope, I've already declared one variable x. So I can't declare another one. If I define a new scope, then I can. All right. So yeah, and so we say here we should. I mean, maybe the better wording would be careful using global variables. Right? So they are often an easy way to do something, but it is what's called a bad code smell in that, if a variable is global, then anybody can change it. And if anybody can change it, you can have bugs introduced in weird places. So one of the things that we're trying to emphasize with object-oriented programming and keeping things private is that we don't want these weird bugs where people access variables that they shouldn't. So global variables, they do get used, but be careful with them. The standard input-output library is how the primary way of communicating with the console in C++. So we use cout to output something. It's a member of the output stream class. Yeah, it's an object with a reference to the standard output. You can actually redirect this to point to something else. For instance, I point this to a string stream in some of the test code for your assignment so that when you print something out, it all gets shoveled into a variable that I can then read and make sure that you've done your assignment correctly. But yeah, so even if I change where cout is directed, that does not change what the standard output is. Printf would still print to the console. There are also these two other members of the IO stream library. Most of our focus is going to be on cin and cout, so standard input, standard out. Cerr, we're not really going to touch upon, but it is not really for application errors per se, right? So let's say in your application, somebody puts in an invalid date. Well, then you wouldn't print the output to cerr. Cerr is more for developers, right? I would put an error message on cerr if somehow data got corrupted and I didn't know how it happened. Then I'd be like, oh, like, please watch out for this error. So it's really communicating with the users of your library rather than the users of your application, regardless. Let's see those examples of those. So I declare two variables int, x and y. I say, please enter two numbers. That goes to the standard output. So now I'm going to read from the standard input, which is typically the keyboard. I'm going to use the stream extraction operator, which is just the greater than symbol. And then I'm going to read into x and y. Now, the nice thing is I can sort of, chain these two operations together so that they happen in one line. The other thing is that this is formatted input, right? Because I'm supplying an int here, this expects to receive an int from cin. So if I don't give it an int, I'm going to, well, bad things are going to happen, right? In particular, I'm going to flip an error bit here. So cin and cout are for formatted input and output. All right, so let's fix this error. Oh, right. It's funny how the error. It said that the error was here. I'm trying to use a binary operation on a string, but the cause of the error was over here where I used the wrong symbol. Yeah, it's funny. A lot of bad or hard to find errors are exactly like that. So please enter two numbers. All right, so I can enter 1, enter, and then it'll wait around for the next number, 5, and there it says you entered 1 and 5. Also, if I want to input it, well, I can just separate them by spaces. So 11, 55, and it says you entered 11 and 55. I can do something like this, 11, 55, 66. It says you entered 11 and 55. What happened to 66? Where is it? Anybody know? Is it gone? You wish. It's sitting on the input buffer. Along with a new line character ready to ruin your life at some point down the road. Right, so okay, so enter two numbers, 3 and 4, and then it says you entered 3 and 4, and now it's waiting for a third number, so I'll enter 6. It says you entered 6. So that sort of goes through a flow that we would expect, right? Every time you see C in, it pauses and waits for you. Let's see if I put all three numbers, maybe it'll make a liar out of me, who knows? But you can see there that I only hit it once, and then both of these C-ins got triggered, right? So you got to be careful with that input buffer. It really is the most trouble I had, like designing the tests for the assignments and things like that, was with this friggin' input buffer. Yes, yes, it is. All right. I believe that's it. You can also use standard error, right? So again, this is not really something we're going to focus on. But you can do this. By default, this will go to the console. Right, so it appears as if it just wrote it here, but technically this is a different output. And so if I redirect standard error to, say, a log file, then you wouldn't see this. This would go to a log file somewhere. And if I take a Python script and I run your code, I can ask for these things separately. I can ask for the error output and the standard output. All right, questions? Okay. All right, functions, methods, subroutines, procedures, these are all other names. This is another feature of C++ and other languages. In C++, we have two kinds of functions: global functions that belong to everyone, and member functions which belong to a class or struct. So in a way, it's similar to, say, I guess JavaScript has global functions and member functions, and so does Python. It really is the most sort of versatile thing. Java does not, right? Java does not have global functions per se, although you can make a class of static functions, which it does, and those behave similarly. C, on the other hand, only uses global functions. There are no member functions, right? So structs are just pieces of data, and functions are just functions. Global functions can be called from anywhere, from any class or any other function. Member functions, well, you can call them on an instance of an object, but you have to pay attention to the access modifier. All right, so function declaration, the function prototype or specification, right? We've seen that. That is separate from the implementation. For example, when we did foo, we gave the compiler a function prototype to let it know that there was this function foo that we were going to use. And this prototype has all the information that the compiler needs in order to verify I've used it correctly, right? Return type, arguments, and name. So typically we separate that from the implementation. The implementation is the body of the function. It contains the code that executes when the function is called. In C++, we like to store these separately. There's good reasons for that around code organization and things like that. It is sort of convenient. So the header has the declarations typically, and the source file has the implementations. Good function design, well, it's arguable, but it shouldn't be too complicated, right? A function should sort of be single purpose and as simple as possible. Don't try and do everything. Make different functions to do different things. It makes things easier to debug, easier to write, and easier to document. You know, they're self-documenting. Functions will take in parameters, process, and return something using a return value or output parameters. So we're going to talk a little bit about output parameters in C++. They sort of are used in other languages. Right. Okay, so good function design. So we're going to sort of, I guess, well, I don't know. I don't know that I necessarily agree with this, but there are, I guess, some schools of thought that think return values should really be used to indicate success or failure and not so much to return values, right? And so that is one of the ways we are going to use return values for certain is we're going to return Booleans that tell the person calling the function whether or not this succeeded. Also, though, for getters, of course, we're just going to return the thing that we're supposed to be getting. Cascading or chaining together functions, which we'll see later, then we're going to use the return value to essentially return the object. Or we can also return the result of a function, right? So we're going to see all of those as we go. In C++, results are sometimes returned using output parameters. So we're going to take a look at that. That is your tutorial 1. You're expected to use output parameters. Yeah. All right, so I'll talk a little bit more about this. Return values are elegant, right? So especially for something like when you take 3007, when you take functional programming, a lot of use is made of return values to sort of chain together elegant code. So that's not that you shouldn't return values using return values. They're simple and intuitive, right? Everybody sort of understands a return value. If I need to return multiple things, I can use structs in C or C++, right? In other languages, you might have a pair or something like that. One of the problems with returning things is memory ownership is not always clear. So in C++, it's important, if you give me a piece of memory, I need to know if I should delete it or not. And in a return value, now I have to look at the documentation to see, when I'm done with this, will something else clean it up or should I clean it up, right? So that you kind of have to be explicit about that. Whereas output parameters are in some sense, well, one of the most common things, if you use the Win32 library, it's written in C or like C, C++ sort of thing. One of the things you do to pass parameters is you allocate a struct, right? You fill that struct with whatever values you want as input. And then when you call the function, you just pass a pointer to that struct, right? And then, well, what can happen is that the function you call can read that struct and it can also write to it. And then when I get the struct back, maybe it has some new values. So that's an example of an input and an output parameter. The nice thing about doing things that way is the memory ownership is clear, right? If I use a struct for an output value, well, I have to create the struct first. So obviously I'm going to delete it when I'm done. When we pass a parameter, we can pass by value or pass by reference. So when we say pass by reference, we kind of mean like pointer, right? Like indirectly. But in C++, we can also use references. So yeah. let's look at the example and then talk about this stuff. I don't want to get too carried away. So here's a new syntax. If you're coming from C, right, is this ampersand. And what it means is essentially, it kind of means I'm passing by pointer, right? In other words, I'm passing by memory address here. But I'm doing it in a way that is syntactically a little bit nicer, right? So references are quite common in C++, so you should get used to seeing them. What this means is that I am taking an int, and when I pass this second int, well, let's take a look at what happens here. So I have an int num and result. I read in num from the user, and then I send that to this check num function. The check num function just declares an int. That means I pass by value, right? So whatever number I type in to num, it gets copied into my check num function, into this n, and then I can verify whether or not it's within the correct range, right? So here I want something between 0 and 100. So I'm going to check this copy of the number. And if it's between 0 and 100, I'm going to return true. Otherwise, I'm going to return false. And that's a typical input parameter, pass by value or pass by reference. It doesn't really matter. But for this output parameter, my double num, I want this to contain the result. So I'm going to take this number n, I'm going to double it, and I'm going to assign it to this variable res right here. This is, I don't really need right now. And then when I return from this function, well, the result was the int that I passed in, but I passed it in by memory address, by reference. So now when I change this variable, this is just an alias for this variable, which means that any changes I make here will be reflected when I print it out. All right, so this is an example of using an output variable or an output parameter. So please enter a number between 0 and 100. Let's say I say 101. It doesn't accept that, but if I do 55, then it doubles it. And you'll notice no return values, right? All I did was pass this in by reference, which means instead of making a copy of the int, I reuse the original int. And then, yeah. Questions? If you get confused, really what's happening is this is a pointer, but the nice thing about it is, or arguably the nice thing about it is the syntax here, I don't have to dereference it, right? I just use it as I would a regular variable. All right. So yeah, here we use Boolean as a check to see if this succeeded or failed, right? So we didn't use any return values here whatsoever. We used input parameters, output parameters, and return values for, well, we used a return value for to check to see if things went correctly. Okay, so let's walk through this. So for example, in my main function, I declare two local variables, n1 and n2. n1 I set to the value 10, n2 I set to the value 8. Right? So imagine these two things are sitting on the function call stack in memory, and they have those values assigned. And then I call this sumMath function. This sumMath function passes num1 by reference and num2 by value. Okay, so if we go over here, put these back in. Well, what's going to get copied? For n2, it's passed by value. So that means, well, I've allocated some space here for num2. And I'm just going to copy the value from n2 in. Sorry, these are backwards. Should be 8. This should be 10. And n2 gets a copy of, or sorry, num2 gets a copy of n2. Num1, though, is passed by reference. So there's a little bit of, I guess, interpretation being done by the compiler. So this is actually a pointer. So you can think of this as actually containing the address of n1. Right? So 00 is the address in this context. And so behind the scenes, really what's happening is this is a pointer, and every time I modify this value, it's going to modify this value. Okay, so here we do num2 equals num2 minus 1. Well, num2 is 8, and now it becomes 7. N2 does not change whatsoever, all right? And here I do num1 plus equals num2. So that means, well, num1 is technically 10 plus 7 is 17, and that gets stored in num1, which is just an alias for n1, all right? So I've changed that value. And then when I return from this function, well, this gets popped off the function call stack, and all that information is lost. However, the result of the operations are still stored in n1. Right, so that's passed by reference, sort of the memory model of it. Any questions? Okay. So we will be doing stuff like that, particularly with objects, because objects we want to pass by reference no matter what, because it's cheaper than pass by value. But the other way to do it is, of course, with pointers. We will focus on pointers a little bit later. For now, I want you to get used to using references. All right, so pass by reference is how we use output parameters. When I want to pass by reference, I'm essentially passing by memory location. One of the ways is with pointers. So you've seen that in C, and you can do the same thing in C++. Powerful, somewhat natural. Easy to make mistakes with, right? You have to dereference it all the time or use the address of. It's kind of a pain until you get used to it. References are they're the same thing, but with like a cleaned up syntax. I don't have to dereference anymore. I don't have to take the address of. They look and behave like variables, and the compiler does all the translating behind the scenes. So under the hood, they're the same thing as pointers, passing by memory location. But in terms of the syntax, we treat it as we would a variable instead of a pointer. That means no dereferencing. It's supposed to protect against null references. So what happens is, well, as we're going to see, when you declare a reference, you have to give it a value right away. It's not like a pointer where you can leave it dangling and not pointing to anything. A reference always has to point to something. So that references will primarily be used to pass arguments to functions, but you can just actually declare a reference wherever you like, right? C++, there are no rules. So I can, for instance, do this. What does this mean? Well, here I make a variable x somewhere in memory, and it has the value 10. And then I declare a variable y, and I point it to x. Well, what that means is that I just give this variable another label. It's an alias for x. So now when I use x equals 8, well, that will change it to 8. And if I say y equals 7, that will change it to 7. Right? So I can take a reference, and even outside of calling a function and passing by reference, I can declare it. So for example, here I have two variables, n1 and n2, and then I have a reference r2, and I'll assign it to n2. I assign n1 and n2 both values, and then I'll print out n1, n2, and r2. And you'll see I have three variables, n1, n2, and r2, but really I only have two values that I'm using. Right, so n1 is 7, which is what we set it to. N2 is 99, which we set it to, and R2 is also 99. We didn't explicitly set R2, but we said it's just an alias for N2. So we can use this alias to change its own value, which in this case also changes N2. So now both of these are pointing to the value 10. Again, there's only one variable there. There's just two references to it. We can do this, R2 equals N1. So once R2 is attached to N2, you cannot attach it to a different variable. It's not like a pointer where I can first point it at X and then later point it at Y. A reference always stays pointing to the same thing, which means that this statement here doesn't have R1 point to N1. It takes the value N1 and copies it into R1 or R2. Right, so in that final step, when I do R2 equals N1, well, N1 is equal to 7. And you can see that when I make R2 equal to N1, it just takes the value 7 and applies it to this variable. Makes sense? Any questions? Early on a Monday morning, I guess. This is not really a chattery time of day, I suppose. So yeah, those are references which we're going to use quite exclusive, or at least for the first assignment, we're going to use them exclusively instead of pointers. So if you use pointers, you're going to lose a couple marks. Eh? Like won't be devastating, but yeah, all right. So let's do a woo clap, finally. So all of that stuff, we're going to just take a little review. Yeah. Yeah. So the idea is no pointers, right? Again, it's not, you'll fail if you use pointers, but you'll be dinged a couple marks here and there. I want you to get used to using references and also statically allocating memory, right? We're going to use the stack almost exclusively. And then for assignment 2, we're going to use more dynamic memory. So yeah, sign in, make sure, please make sure your name is there. If you're not using the, the single sign-on from Carleton. If you use a single sign-on, it's fine. I'll be able to identify you. If you don't, please put your first and last name. What is an object file? Oh my goodness, what did I? Oh, I guess I left this one open. So how would you describe an object file, I suppose, right? Again, I think, is this going to do a word cloud or something? There we go. Machine code. Well, now you got a hint. So yeah, a lot of people like machine code. Computer readable code. The step before machine code. Yeah, so there's no filed code linked. Yeah, so machine code is probably the most accurate. The step before machine code, it's still technically machine code. It's just you can't execute it because it's not complete, right? You still have to link it to other machine code typically, or if not that, you still have to turn on you have to flip the execution bit. So yeah, unlinked machine code, that's a good one. Yeah, so good. So you guys seem to have a good idea of what that is. Excellent. Questions? All right. What is linking? Oh, multiple choice. Compiling a source file into an executable, compiling a source file into an object file, assembling object files into an executable or running an executable. Yeah, so I'm not fooling anybody here. So yeah, number 3 is the most correct answer, right? So linking is typically taking object files which are already compiled into machine code and just linking them together, basically by matching up function calls to their memory locations. That's very good. Oh, match these up. Match the area of memory to its correct description. So we got the 4 main areas of memory that are allocated at startup: code segment, data segment, function call stack, and heap. And what is the best description of those? Or I guess, which section of memory would these go into? All right, so let's see. Code segment, users compiled code. So yes, the users compiled code would go into the code segment. Global variables and string literals, those are going to the data segment. Local variables of a function, memory address to return to when complete, those go on the function call stack. Memory return from a system call, those go on the heap. So yeah, most of you seem to have a pretty good grasp of what these areas of memory are used for. Some of you got it wrong, that's all right. This is, this is meant for learning. This is just a way to sort of review and refresh. See if there's any obvious errors here. All right, now just some. All right. What would the following expression evaluate to? Right, and I guess the hint would be remember bed mass. This does not get evaluated from left to right. Oh, lots of fives. Minus 14. That's interesting. I don't know. 2 minus 3. Minus 1, 12, yeah, I don't know. Well, 5 is, of course, the correct answer. So this would get evaluated first, divided by 2. That would give us 6. And then 2 plus 6 is 8, minus 3 is 5. So yeah. All right, that's good. What is the value of the first x in this piece of code, right? So where it prints out first x here, what is the value that's going to be printed? I give multiple choice? No. Somebody says 8. A lot of people say 8. And yeah, if we look at the syntax, right? So this is shadowing this. So if we just say, well, print out x, it's going to look at the x that was declared in this scope, right? If it has a choice between 2 x's, it's going to take the one that was declared locally. All right, so 8 is correct. What about second x? What is this going to print? Yeah, this is basically the example we just did. Let's say 8s and 5s and wait, what is second x? Second x is going to be 8, right? So here I am declaring a new x every loop, right? Now it's, of course, the compiler is smart enough, it's going to reuse the same memory location, but technically speaking, this is a new variable every single loop. And then once I exit the final time, this gets destroyed. And when I access x, it goes again to the, if it has multiple ones to choose from, it goes to the one in its own scope. So yeah, last x would be the last one. And so what is the value of last x? Well, here we're using a special notation now. The scope resolution operator. Oh yeah, so I'm not fooling anybody. So yes, the scope resolution operator automatically accesses the global variable, x. All right, and we'll see that, so although global variables are frowned upon, in C++, you can declare a global variable, but it's going to be local to this file, right? So I can have global variables that are still sort of hidden from the rest of the program. So that would be the place where you would most often see this sort of syntax. All right, very good. So yeah, that's it. Any questions? Right, woo clap number one. Sweet. All right, that brings us to programming conventions. Incidentally, this is, right, so wherever you work, they're going to have sort of style guides that you should follow, right? So that's all this is really, is it's about style. And it's important that you're on the same page as your colleagues so that when they read it, they can understand what you're trying to communicate, right? So it makes code easier to read, makes interfaces consistent, right? Helps you to communicate. Some naming conventions are universal. Well, we say universal, but then somebody's bound to break these rules somewhere. Also, this is sort of, I don't know, man. Large language models are going to sort of make this obsolete because now if you're always generating code, it's going to generate it with the style that is supposed to be there. So actually, you'll still have to know the style guide, but again, you guys, when you're working, you're going to be, what you're doing is going to be vastly different from what I learned. You know? I'm like rattling my brain too, trying to think of assignments that I could give you that could use large language models, but I don't know, it's a tough problem. Because what if you're using, right? I could design it and test it on, say, ChatGPT, but then somebody might use something else that can solve it very easily. So it's a hard problem. So a lot of your classes, you're going to see dancing around this issue, which I'm dancing around it, you know, and making you run COMAS on your machines and show up so they can see that you're programming, so they can see that you're learning something, because the only way I know how to do it right now, I'm trying to figure out other ways, but no luck so far. So yeah, large language models, it's really going to be different. You guys are sort of almost, I would say, pioneers, right? So some of you are going to go out into industry, use large language models, and then come back and then teach and have some effective teaching strategies. And that might be, we might be waiting until then before we get them. Some naming conventions, constant names are all uppercase. This is one of the most common ones. If you see all uppercase, it's most likely a constant. If we need to separate words, we can use an underscore. Variables typically begin with a lowercase letter. Camel case or underscore for multiple words. Again, though, syntax highlighting is sort of right, taking away the need for this sort of discrepancy. So you'll often see variables that start with capitals. You'll often see classes that start with lowercase letters. Name should be self-documenting without being overly long. Right? If I'm storing a name, use name, don't use n. That can get very confusing. You can use the scope as context. I don't always need student ID, although I'm not going to carry a big stick on that. But if I do have an ID in the student class, I could just use ID, and I know that it's a student ID. The class name will provide the additional information. For looping, we generally use lowercase I or J or K or L if we have more nested loops. For this class, data types and classes should begin with a capital. Now, you'll be using a class, let's say string. In C++, it starts with a lowercase s. So even the standard template library breaks this rule. But for our class, the naming convention should be capital. You can use camel case or underscores for a compound name. I tend to mix them up, which is actually kind of a bad thing. I should be more consistent about that. Functions should begin with a lowercase letter, and you can use camel case or underscores for compound names. Names should be as short as they need to be descriptive, but no shorter. And if they're long, there's no penalty for that either, right? As long as it's descriptive. Indentation, you should sort of adhere to the Python ethos, which is, well, Python, you have to indent. But you should aim to do the same thing in C++, even though technically the The braces define a block, not the indentation. But for reading purposes, I get to see that, hey, all of this is in the same block. I don't have to start looking for these little braces. So a nested block is a block within another block. And so if I do that, I should indent an extra. And basically, all blocks at the same nesting level, right? So they might not be within the same block, but if they're like nested 3 blocks deep, then all of those should have consistent indentation. And that's kind of easy with IDEs these days, because you can just select all and then apply some universal fix, and it'll indent everything for you and make it all look nice. All statements within the block should have the same indentation. All blocks, yes. So I just mentioned that. The 3 styles are here. I don't know, choose whatever one you like. Try and be consistent, I guess. But I like this, but sometimes if I'm using autocomplete, I might get something that looks like this. Again, I rely a lot on the IDE to fix all this stuff up for me later. If you have one line of code in a block, you can do everything on the same line. It's also fine. How much should you indent? Just try and be consistent, whatever you choose. 2, 4, 1 tab space. Comments. All right, I don't carry a big stick on comments, especially in this class. There's a few reasons for that. One, if you're commenting all of the functions and classes, you're basically just copying what I already wrote in the specification. And I don't need you to do that. That's just busy work. Also, I'm not a huge fan. So yes, at the top of your class, you should explain what your class does, right? Or a complicated function you should explain there. But if I'm seeing big blocks of comments in your code, then I think you've really done something wrong, right? Your code should be readable. I shouldn't need a huge block of code. And it's also messy. It just looks terrible. And now if you change the code, you got to change this huge block of comments. So for me, comments, like less is more, right? Brevity is the soul of wit. And so less words is always better if you can get away with it. That, on the other hand, if you have to put a comment, don't be afraid to, right? It's you're communicating with other users of your code. Well, actually, you're communicating with the TAs. So bear that in mind. Like, there's actual people that are going to read your comments. If you feel like you need one, put one. You're also communicating with yourself, right? If you put this down and then come back a few days later, sometimes it can help you understand what you wrote. So yeah, I'm not gonna carry a big stick on comments. You should use it to make sure the TA understands your code and that you understand your code. Other than that, I'm not going to enforce it. I also find a lot of TAs, it's very inconsistent, right? Some TAs are really, well, they just all marking differently, it seems like, no matter how many times you tell them what they should be doing. So types of comments, inline, right? So something like this would be sort of valid in this situation. I'm just extending the line here. If I have 1 or 2 lines, then I can just use the 2 forward slashes. If I need something bigger, then I can use this larger block style of comment. Typically, I would reserve this for the beginning of a class or something like that. Other conventions. Again, every rule that we tell you to follow here is broken somewhere if you look at C++. So don't use struct when you should use classes. In this class, we're using classes simply because we're trying to enforce this principle of least privilege. Don't use global variables unless you have to. Again, they are often used at file scope and hidden in that one file. So don't use them, but if you have to, then if you have a good reason, if you can justify it, then go ahead. Don't use too many global functions. Again, so I've crossed all 3 of those out because I've grown more flexible on them, right? There are many valid places to use global functions. Sometimes you don't want to make a whole new class just to make a function. Just make the function, right? Don't pass objects by value. that is a good rule of thumb. And we're going to be enforcing that. It's a really bad idea to make copies of objects every time you pass one to a function. Objects should be passed by reference. Reuse code when it makes sense. Perform basic error checking. You will be actually evaluated for this, right? So if you have a date class and I try to set the month to 13, you should not allow that, right? You should double check and make sure. And then I'll get questions like, well, what should I do instead? Just do something sensible, right? Make a date that is valid. Maybe it's not what the user wanted, but they'll figure it out, right? Solve problems in the most simple manner possible within the guidelines giving, right? So there's often the temptation when you start seeing design patterns to use them everywhere. Sometimes your problem is solved by introducing a getter. And if your problem is solved by introducing a getter, then just introduce the getter, right? Don't do the fancy thing, because nobody's going to understand it. It's going to be a bug that you're going to be debugging at midnight on a Sunday night, right? If a getter solves your problem, then I say that's a good day. Solve the problem with the getter. And then everybody understands it. It's not fancy and too fancy to debug. This is, I would say, my rule of thumb, is that simplicity is what you should be aiming for. At least I find I've had the most success with that heuristic. All right, questions? Okay. All right, so finally we'll get to some classes. So we're going to talk a little bit about, we're coming from a C background technically. So we're going to take sort of a piece of C code and translate it into object-oriented code, just to see sort of the differences and similarities. And then we will talk about classes specifically and access specifiers, class members, how we organize our code around classes, scope, and namespaces. And so yeah, namespaces is your tutorial 2. I expect we'll get to it by the end of next class, but if not, you do have an extra week for that one. So C++ was once known as C with classes. So it's basically we take C and then we apply this object-oriented paradigm. So what is this object-oriented paradigm and what does it offer us? Well, it basically offers us a way to encapsulate code and keep things hidden that we want hidden. All right, so let's take a look at this example. So this is, I mean, it's C++, but it's sort of a very C flavor, right? So I have a struct, which is a student. A struct by default, that means all of these are public, so I can access these members from anywhere. I have a print function, and then I have a main function where I declare an array of student objects, right? So, I mean, this might be sort of important. What precisely is that array? So our student, if I can draw a simplified one, well, it's 3 strings and a GPA. So if I let's say tried to draw this in memory, this is a student, it has a name, which there's some string, it has a number, there's some string, and then a GPA, and then something else, whatever. The GPA is a float. Okay, so that's what so in memory, that's what it looks like. I have 2 strings or 3 strings pushed together along with a float. Now, when I make this array with this particular syntax, this is called a statically allocated array of students. What that means is that the array goes on the function call stack, and each location in the array is a full-fledged student object. So if I look back here, my array would look something like this. Say it was 3 students big. Well, then each of these would be a student, and each of them would have 3 or 2 strings and a float. and so on. Okay, so that's basically what we're looking at in terms of memory model, as opposed to an array of pointers in which there would be no students, there would only be pointers, but yeah. Questions? We'll cover this in more detail later, but just to make sure that we are making a correct memory model. Then I might have a bunch of initializer values, let's say that I get from a database, but here we're going to mimic that by just making some arrays. We can initialize all the students. Name, number, major, and GPA are all public, so I have direct access to them. And then when I print them out, well, I call the print function and I pass a student object to it. And when I print out all the passing students, well, I just check to see if their GPA is less than 6, and if so, I skip them, and otherwise I print them out. So all right, so it's kind of all right, it doesn't want to cooperate. Terrible formatting, but here are all my students, Joe, Amy, and Barb, and then all my passing students are Joe and Amy. Okay, well, that's typical C code, nothing special about that. But what we want is, well, there's a few things that we want. Number one, for classes, instead of having a function that takes a struct as an argument, we're going to put this function, we're going to add it to the class. And then down here, instead of directly accessing this GPA and testing to see if it's less than 6, I kind of want to hide that, right? Because this is an implementation detail. Now, if at some point I change the definition of a student passing, like for instance, Carleton has a 12-point scale, but you go to another school, they might have a 4-point scale. That means I have to go through all my code, and everywhere where I see this, I have to change that. And I want all changes localized, right? So functions are very good at that. So, right, so I should, at the very least, put this in a function. But I'm going to do it one better. I'm going to, well, I'm going to take my print, for example, and move it from a global function to a local function. All right, so that means I no longer have to pass in the student explicitly. And then down here, when I call print, instead of calling print student, I call student.print. Right, so it's just really a sort of superficial and a syntactic difference. In terms of the code that's generated when I compile it, it's exactly the same. Right? C++, the goal is, what do they call it? Zero cost abstractions. So when we put this extra sort of structure around our code, we don't pay for it in terms of runtime. When it's compiled to the exact same thing that C would be compiled to. Right? So all these abstractions disappear. These abstractions are just to make our life easier. But let's take that a step further. Well, this initialization step, I also want a function that initializes them. And of course, I also want a function that checks the GPA. So if I look, well, now my class, I have a constructor. The constructor is going to initialize these member variables. I have a print function that operates, right? So these I have access to, and I don't need to pass in a student explicitly. I have my isPassing function where this is now nicely hidden away. And all this allows me to do, or one of the benefits that this allows me to do is now I can make these member variables private, which means that you can't grab the GPA and change it to pass, right? You have to call one of my member functions, the publicly available member functions, say change GPA. And now within that member function, I can say like, oh no, I'm not changing your GPA. Like I double check your marks and you didn't pass, so your GPA stays the same, right? So this makes sure that people that shouldn't access these variables don't have access to them. And that's really one of the major differences between imperative style like C and object-oriented style like C++, is that I'm hiding data. And now I give you a public interface which consists of this public function, and this public function. And you just call those functions, and that's all you can do. You can call the function and ask, like you can ask me to print this, but in here I can decide, oh no, I don't want to print it for whatever reason. So yeah, it gives us, well, first of all, now we have data and behavior about that data, but we also have protection for our data, right? So that's sort of the underlying philosophy here is encapsulation. And you can see that the code runs exactly the same, right? And so that is that idea of zero cost abstractions. Even though we've added extra structure and now we're, so that we can do fancier things and make our life easier, it still compiles to the same thing. And in fact, if you looked at it, it would literally, right, this print function would literally take a student argument if you looked at the assembly. Okay, questions? Okay, so that's the philosophy behind what we're doing. Let's look at some of the details. Right, so both imperative and object-oriented programming have data, right? So we can store data in structs or classes and functions that operate on that data, but in object-oriented programming, well, those functions now become part of the object. Object-oriented programming also makes encapsulation natural and easy. And encapsulation is I make my data private, and the implementation of my function is sort of inaccessible to you, right? So you can call my function, and I can do what I need to do, but at no point, right, I can always double check to make sure you're not corrupting my data. So the functions decide when and if data is modified. If you try to set the month to 13, obviously I'm going to say no, but maybe I'll set it to 12, assuming that you meant something like that. All right. So we've seen some access specifiers, public and private. And so we'll talk a little bit about that and why we want to make things private, right? So typically industrial grade software is huge, right? Windows is millions of lines of code, literally. Arguably, some of them are not needed, but millions of lines of code, hundreds of libraries and packages. This is difficult to manage, right? When I go through and say, I need to fix a bug, I'm going to make changes here, and like maybe I'm not certain if I should make them over here. Well, if things are private and sort of behind a public interface, then that's going to protect me from making those types of mistakes, right? I'm going to only be able to modify the things that I should be able to modify because when we wrote the code, we applied this principle of least privilege. So everything we could make private, we made private, and we only made things public when we had to, right? So, for example, your car has a public interface, right? It has a gas pedal, steering wheel, and like ignition. And so how does, when I turn the wheel, it makes the wheels, I've turned the steering wheel, it makes the wheels turn. How does that work? I mean, I don't know. I don't know, and I don't need to know. Right? So that's the difference really between public interface and private implementation details is, well, the public interface makes driving easy. If I had to know every mechanical detail of that car, I would never be able to drive. But because I can steer a wheel and push on a gas pedal, driving is sort of simple. The car itself is complex, but I don't have to worry about that complexity. Right? So that's sort of what we're trying to do with our software, is we're going to give you a nice, easy-to-use interface. We're making, say, a library. And you're going to use that interface, and you're not going to worry about what's behind the scenes, right? I'm going to fix all that up for you and handle it, because in this case, like, I'm the mechanic. So yeah, a member that is public is visible to all objects and global functions. We can also make members protected. So this is visible to subclasses only. This is different from Java. Java, I forget how Java has a default, right? If you don't put any, and then a protected, which is package level, I think, but I could be getting that wrong. In C++, it means something different. It's only for inheritance. So protected means my children get to see these member variables. Private access is it's not visible to anybody else except for me, right? Well, it's also visible to members of the same class. In Java, it's not. If I make something private, right? If I have a student one can't see the GPA of student two if it's private. But in C++, they can. So we'll see this is going to help with things like copy constructors. So when we make a class, we use the class keyword followed by the class name, followed by braces, followed by a semicolon. And then we'll have different blocks of access, right? So for example, if I make a student class, it would look something like this. And then all of the public functions and or variables would go after this public declaration. And then I can declare private, and all the private member variables go there. If I put anything up here, these are private by default, right? If I don't have any declaration, everything in a class is private. When I declare an object, a class, well, there are a couple ways to do it. Same as when we looked at the int, right? An int, you could statically allocate it, int x, or I could dynamically allocate it by calling new int. Well, I can do the exact same thing with classes. So here I've statically allocated two instances of students, one that called a two-argument constructor and one that called a no-argument constructor. Yeah, so all right, let's come back. We only got 2 minutes, eh? All right, so this is statically allocating an object. So this is what you're going to be again, for assignment 1, this is all you're expected to do. I should not see new anywhere, right, in your assignment 1. So anytime you want to declare a local object, you're going to declare it statically like this. And typically, if this was in a function, of course, it goes on the stack. You can also declare it within another class, and then it's declared in that context. But for here, we will assume that this is on the stack. Statically allocated means that when the stack frame is popped off, the object is deleted for you, which is nice and convenient for us. We don't have to manage memory explicitly. It's going to get handled for us. You can also allocate objects like this. This is dynamic allocation. You see the new keyword, that means it goes on the heap, and it returns a pointer. Again, for assignment 1, we're not really going to focus on that. This will be an assignment 2 thing, but it is good to sort of introduce it to you now. This goes on the heap. The heap is a lot slower, but of course, we have full control over when these things get deleted. All right, so you'll see that we should break down classes into header and source files, but we'll pick that up next class. So we'll stop there for today. So yeah, get your tutorial 1 in. I will extend tutorial 2 until next weekend. Even though if you want to do it by this weekend, it shouldn't be a problem. But yeah, that's it for today. I'll give you more information on the test when I have it. But yeah. Either way, it'll be written. There will be code. You'll either handwrite it or type it on your computer. Hey. Yeah.
I'm just turning this on. I ran into an issue with submission. I tried using the Python, I guess, file to
Okay.
like grade it, right? And it gave me a 10/10.
Okay.
But when I tried